Derivation of the equations of motion, number 2. Of course, that constant acceleration is very important. Here's what this equation says. We have displacement equals the average of velocity and velocity original multiplied by time. Again, you've had an opportunity to rearrange this equation algebraically to solve for every variable and evaluate it, but now we'll put meaning to it in context based on what we know about motion and motion graphs. The best way to approach this particular equation is to look at a velocity versus time graph. All right, so let's say we have an object that is accelerating constantly at a constant acceleration. How do we know that? Well, this slope here on a v versus t graph has to be straight. If it's curved, then we don't have a constant acceleration. So it's got to be a constant value. So here we go. We have that. I've got a value v naught over here and v over here. All right. So what I'm going to do is shift this around a little bit. I wanted to show you the slope. However, what I'm going to do is actually begin this at v naught. All right. So we have some kind of initial velocity, but this slope from here, this guy has to be straight. Okay. So we have two parts here. We have this kind of trapezoid looking thing, and we'll call that t. All right. So how do we analyze this? Well, we got some shapes, and we know how to deal with the shapes and what their meaning is on a v versus t graph, because shapes, the area underneath them, bounded by the time axis, the 0 here, is going to give us displacement. So for example, down here, we would have the rectangle, and up here we have a triangle. There's another way to approach this, though, to make it a bit simpler. So instead of finding the area of a trapezoid, why don't we do this? Why don't we check it out and make it a little bit simpler? So I can say, what's the value between v and v naught? Well, we know that that's the average value. It is actually this over here. If you take any two numbers and want to find their average, you add them together and divide by 2. So here it is. This expression over here, in parentheses, is this average of velocity and velocity original. All right, so what I'll do is dot this across, and this value is v plus v naught over 2. It's the average of the two. And what I'm going to create in green here is this large rectangle. Okay, that large rectangle, the area of this rectangle, which is very easy to find, it's just base times height, is going to give us the results of this equation over here. It's going to give us the displacement. Okay, so what we have here then is base times height. Well, this part is the height. V plus v naught over 2 is the height over here. So height times base, which is time, times time, gives us displacement, like so. You could also do this in two parts, which is totally fine as well. You could do it where you look at the area of this rectangle here. We have that is v naught, okay, times t, plus the area of the triangle, 1/2 base times height. Well, what's the value of this? Well, what we have here, in that case, is 1/2 base is time, and the height of this triangle is v minus v naught. So it would come out the same as this over here. I just think it's a little easier to think of it in terms of how we initially approached the help of Phineas and his amazing abilities. We did the average of the two velocities to find out that the average value of v and v naught, and then over the time interval, we multiplied by the time interval, and we got how far he went. So really what we were doing when we did the patterns and proofs initial activity was finding the area underneath the shape over here with the average velocity, and that's how far he went. Okay, so that's this equation over here. D equals v plus v naught over 2 times t. Again, it comes from analyzing the shapes within a velocity versus time graph onto number 3, equation number 3. This ends number 2. We're going to 3. We're going to bring this back, though. It's going to help us for the next one.